So hi and welcome everybody. Welcome back to the second part of the tutorial on Open RAN systems. So continuing from where we left off, here we have the Open RAN overall architecture. As you can see, you have many different components here, but I want you to focus on the 5 main components of Open RAN. Beside the interfaces. Don't confuse yourself with the interfaces for now, but just focus on the components that I'm gonna mention to you. The first component, you have the Open Radio Unit, which is here. If you look on the right-hand side figure or picture, you have here the open, at the bottom, you have a box colored, like rectangular box colored in orange. You have the Open Radio Unit, which represents the physical low layer, mainly RF. This is the radio remote unit that I showed you in the previous lecture, in the previous tutorial. So you have the radio remote unit, which is consisting of a DAC and DAC and some physical low layer functionalities like I50 and D50 filtering and so on. After that, it's connected with Open Front Haul with the Open Distributed Unit. This is kind of the PP unit, baseband unit, which include the functionalities of the higher layer with the functionalities of the physical high layer. As you can see here, physical layer is split into two parts, low and high. The low is integrated with Open Radio Unit and the high is integrated with the Open Distributed Unit. And the reason for this split is to reduce complexity and lower the cost of the Open Radio Unit and drive innovation to be happening in the software. Beside the physical high, you have the MAC functionalities, scheduling, automatic repeat request, assigning resources, and other functionalities of the MAC. Plus, you have the radio link controller, RLC, radio link control. Now, you have the Open Radio Unit, Open Distributed Unit. After that, you have this Open Distributed Unit connected via interface F1 to the multi-rat CU protocol stack. So you have now this whole PP unit is connected with the control unit for the control plane and the central unit for control plane. CUCP means central unit for control plane, and CUUP means central unit for user plane. Now, what's the difference between control and user? User plane represents the data that you sent over your network, the actual data that you are transferring and sending. CP, the control unit, contains the signaling, the handshaking, those messages that provide information about the communication and the procedures that you need to establish before you actually start sending or receiving your data. And this can be multi-rat. Multi-rat means multiple radio remote unit, controlling multiple radio units from different vendors. You can control them from here. The CUCP here consists of control functionalities. You have the RRC and PTCPC. So the RRC, we talked about it earlier in one of the lectures, remote radio control, controlling the resources, and physical PTCPC is the packet data convergence protocol, which is for control purposes as well. Now, this control layer, plane is connected via interface E1 with the CUUP, central unit user plane, which contains SDAP, and also PDCPU, Packet Data Control Protocol for user plane, and SDAP. Those all together in one layer connected via interface E2 with the RIC. RIC here stands for RAN Intelligent Controller, near real time. The functionalities of this block are happening in real times. And this contains what? You can think of this as the application layer, and it contains third-party applications, APP applications, radio connection management, mobility management, quality of service management, interference management, the trained model. All these management and mobility things are happening in the RIC, RAN Intelligent Controller. You can think of it as the brain of the Open RAN system. Now this Open RAN system, the RIC, is connected via interface A1 with the orchestration and automation, which is at the upper layer here in purple. This layer, orchestration and automation, is responsible for configuration and controlling the whole Open RAN system, design, inventory, policy, even running some machine learning and artificial intelligence technique to extract some knowledge and utilize it to optimize the network. So this is the structure, the architecture of Open RAN in a nutshell. And if you look on the left-hand side of the slide, you will see another picture that clearly shows you how the interfaces are connected between different components of the Open RAN, starting from the Open Remote Unit, Open Distributed Unit, Open Central Unit User Plane, Open Central Unit Control Plane, connected via different interfaces with the near real-time RAN Intelligent Controller. All together are connected with the service management and orchestration framework, which is the functionalities there are happening not in real time. So you can see different interfaces here. All these interfaces are open interfaces, not closed. Anybody can connect his software or his solution with them. So there is nothing there is nothing to worry about in terms of incompatibility. So all these things are supposed to work seamlessly with each other. And once you have a solution, you need to decide where your solution is going to be functioning. Is it in the Open Radio Unit or Open Distribute Unit or near real-time RAN, or is it a machine learning AI method that optimizes your network? Based on this, you decide and you see where your solution is gonna be working. But this is the overall structure. So the interfaces, if you look at this, and let's just explain the interfaces to you here briefly. For example, A1 interface connects the near real-time RAN with the non-real-time RIC, which is responsible for service management. So it's basically interface A1 between service management orchestration framework and near real-time RAN Intelligent Controller. Interface E2 is connecting the RIC and the Open RAN nodes. Open RAN nodes, they include the OCU and ODU. This is E2, interface E2. Interface E1 is connecting the OCU with the OCU CP with the OCU UP. The interface, which is like the control, connecting the control with the user data. F1 is connecting the OCU with the ODU. F1 is connecting the ODU with the OCU. And open front hole here, open front hole between the two red blocks here, it connects the ODU and ORU, the remote radio unit with the distributed unit. And O1, you have interfaces O1, O2. O1 supports typical FCA, PC, and other management functions between the ORAN components and the service management and orchestration framework. As you can see, it's O1 is connecting the open eNode P with the orchestration framework along with services and service management. O2 supports virtual resources. O2 is connected with the cloud. So if you have a solution that's running on the cloud, you can connect it via interface O2. Here here you can see that more details are provided for each layer for the service management and orchestration called SMO, for the RIC, near real-time RAN intelligent controller, and the interfaces and what they do and what they connect, the multi-RAT CU protocol stack, and the ODU and ORAN radio unit. So exemplary use cases of this architecture, it can be used for it can enable us to have the following things: context-based dynamic handover management for vehicular to infrastructure, quality of this QoE optimization for optimizing the whole network and providing the best performance after you train your network using AI and machine learning model. And you have flight path based dynamic UAV resource allocation. Those are some examples of use cases for the ORAN. And the use cases also include traffic steering, massive MIMO optimization, radio resource allocation for UAV application, and the quality of service-based resource optimization and allocation. So all those are different functionalities. And here in the Open RAN Alliance, you have, I told you it's Open RAN, the Open RAN Alliance has more than 400 or 500 companies all together working to build Open RAN solution and to divide the work among themselves, among each other. They split themselves into different groups, 8 groups. We have the work group 1, which is responsible for defining the use cases and overall architecture of Open RAN. We have the work group number 2, which is responsible for defining RIC and A1 interface, and work group 3 responsible for RIC with the E2 interface, work group 4 open front hall interface, which is between open radio unit and open distributed unit. Work group 5 responsible for the issues related to the interfaces F1, W1, E1, X2, XN. Work group 6 is responsible for defining reference designs that enable the decoupling of RAN software from hardware platform, its cloudification, virtualization, and orchestration. Work group 7 is responsible for defining hardware platform that combines commodity components and reference design that enables that platform. Basically, they intend to build white box hardware. And the work group 8, which is the most important group, I believe, because it's responsible for building RAN software and they provide it in an open source manner. Think of this like the output of this group is going to be a software that looks like SRS RAN or OpenBTS or Open Air interface. Open RAN has selected a single split point known as 7 dash 2x. You know, in 5G, in the 5G standard defined the possibility of providing, of adopting or using different splits. What we mean here by split, split means putting certain functionalities of the stack in certain boxes and provide them as a solution. And you are free to choose any split you want based on your requirements and your features and the things you are going to be deploying. But the split that's considered by Open RAN is 72x. And this split says the following. You have the physical law plus the RF are going to be in one split, one part under the open radio unit. And the other part of the G node B is going to be in a different solution, which include the physical high, the MAC, the radio link control, the packet data control protocol, RRC, and this DAP. So this is the split. What do we mean by this? The open radio unit is gonna have analog to digital conversion, FFT, IFFT, digital beamforming, but it's not gonna have the responsibility of equalization or layer mapping or modulation, demodulation. So the lower part of the figure here on the left-hand side is gonna be for all these functionalities are gonna be added together as an open radio unit solution, and the upper functionalities are gonna be in the distributed unit and control unit. As you can see, modulation and demodulation is gonna be in the open distributed unit, which means that you can use this in the baseband unit. And this whole structure explains better it shows you different types of splits, and it clearly tells you, for example, split 7.2. This is split 7.2 happening at physical layer 1. It's not even, it's splitting the physical layer into 2 layers basically. The RF and some IFFT and filtering approaches are going to be in one part, the radio unit, and the others in another point. You have split 8, for example, the RF unit only in one part, and the other are going to be a different solution. But this is usually determined by the company based on features, requirements, and capabilities and cost and latency and other parameters to look after. Here we have in the split that Open RAN adopts. In the split that Open RAN adopts in the system they are building, we have the possibility of using precoding in the open radio unit, and the possibility of using precoding not in the open radio unit, but in the open distributed unit. So they make this as a flexible functionality, a flexible tuning parameter that you can use and adapt according to your needs. So basically you have precoding, as you can see, in the open distributed unit and open radio unit. If you use precoding in the open distributed unit, you should pass by, you should skip the precoding in the open radio unit. If you include, on the other hand, if you include precoding in the open radio unit, you should skip the precoding step in the open distributed unit. And all the ones and all the dotted blocks are optional, are not mandatory, but they are going to be used for specific functionality to improve your network performance and system parameters. And this is the Open RAN split functional 7.2x. As this is just a slide replicating the previous slide, just in a different just giving you a different look on the split. Where is it happening? So the precoding functionalities here, and the Open RAN lower layer downlink split description, and where the precoding and beamforming are happening. And this is a more comprehensive view of the split between the open radio unit and the open distributed unit, where each part is showing you open radio unit is representing the physical low and the open distributed unit is representing physical up. As you can see, we have different types of signals. Yes, we have physical random access channel signals, which you send them at the beginning of your communication. You have SRS signals, sounding reference signal, which you send them for channel estimation purposes. And you have the physical uplink, physical shared channel, physical uplink, shared channel, physical uplink for the uplink and downlink. And this is basically representing the data that you actually transmit. As you can see, you have scrambling, modulation, equalization, IQ compression and decompression. And all these blocks are distributed among these two physical layers, up and down. This slides talk about the synchronization issue in Open RAN and how it should be done. It says that some synchronization functionalities has to be happening between the devices in the ODU and ORU in the front hall, and gives more detail about it. Air interface frequency error. It gives some conditions on this synchronization, that the error should not exceed certain values, so that it can be regarded as compatible with the standard units. So in this slide, we summarize the differences in the core between 4G, 5G, and Wi-Fi. If you think of Wi-Fi deployment, it's basically the easiest to deploy. You just buy a Wi-Fi router, you plug it into the socket, and you have a wireless access. You enjoy the capability of connecting with the internet. But if you have 4G network, the 4G network is not that easy. You have, beside having a wireless head eNode B, you have also a core, and this core, we explained it in previous lectures. It has packet serving gateway, packet gateway, which is responsible for transferring, sending, and receiving the user plane. And you have a control plane, which has the functionality of mobility, home service subscriber information, mobility management entity, and PCRF. Now, if you go to the 5G core has the same functionalities as the 4G core, but there is as you can see, the names here are completely different from the 4G. So there is renaming, rebranding of the functionalities happening inside the 5G core, but basically they are doing the same functionality. They are achieving the same goal. But the user plane, this is one thing I want you to notice, the user plane is going through the user packet functionality, UPF. The other ones, which is AMF, AUSF, SMF, BCF, UDP, all of them are for management purposes and control in the control plane, and they are not for the data, but rather for the signaling and control messages. Now, we have some free implementation for the core. One of the most common implementation is the Magma implementation, which we talked about it earlier, and the 5G core free, and some other implementation. So Having talked about Open RAN, now let's talk about the general picture of a 5G network, a private 5G network that you want to build for an enterprise or a company. So you have the devices, the user equipment devices, which can be chips, Internet of Things devices, cars, drones, or whatever, connected with RAN software. And this RAN software is the software that's going to be developed by Open RAN or SRS RAN or OpenPTS or Open Air interface. It's an open source software which has the functionality of the RAN. Connected with a micro cloud, you can provide your software as a service over the cloud. And this is going to be connected via EPC, the core, which also we have some open source implementation for the core. Most importantly, and the most famous one is Magma, and this can be optionally connected with a public or a private cloud network. This is just replacing these figures with the solutions that can be used in order to build this network, with the exact names of the technologies that you should use in order to build your complete end-to-end 5G or 4G network. Now, since the establishment of Open RAN, many companies jumped into this ecosystem and this business, trying to provide solutions, softwares, products, hardware, services, integration, from system integrators to software suppliers to hardware, software supplier, CU and DU hardware supplier, secure supplier, virtualization, virtual environment suppliers, and chipset suppliers. And those are examples of the companies who are involving in the Open RAN and producing products to the ecosystem so that operators and internet service providers can buy from them. And note that this list is not exclusive. There are many other providers and vendors and companies which are not included here, because some of them they participate in conferences, some they don't participate. So this list is just for those who participated in the Open RAN exhibition show, which happened in 2021 recently. Now, for those who have still doubts about Open RAN, I want to emphasize that Open RAN is already a reality happening, and there are many deployments around the world. As you can see from this map, you have the companies in USA which adopted Open RAN and deployed it, including Dish, Altran. This is in US, North America. In South America, we have Telefonica deploying many different Open RAN based solutions. In Europe, we have also several deployments in Africa, in Asia, even in Australia. There are all around the world. There are many deployments and innovation is happening, and people are moving towards adopting and using Open RAN instead of the closed systems that prevent them from adopting the latest technologies and reduce the cost to minimum value so that their solutions and their services can be affordable by their customers. So, having talked about these things and the emergence of Open RAN and the deployments and the companies backing up Open RAN and providing solutions, one thing I want to emphasize is that Open RAN was developed while keeping in mind that machine learning and AI can be key technologies to reduce the complexity of managing the networks and optimizing them. And this slide shows you the core area, the fields and the part of the networks that machine learning and AI can be used in order to improve the overall performance and reduce the cost, reduce the headache, reduce the manpower, and make things work seamlessly. because in 5G, as the technology advances, we currently have 5G. In the future, we'll have 6G. And the more features you add to your network, the more capabilities, the more parameters, the more complexity it will involve. And it will be very difficult to train people to master the field of optimizing these parameters and having full knowledge on all of them. It becomes really hectic and impossible to cope up with. So one way to reduce this headache and to make sure that our networks can work seamlessly and run smoothly is to deploy machine learning, to come up with new methods, new techniques that can minimize the headache of running a wireless cellular network and make the management seamless. So machine learning and AI are potential technologies that can be used in order to achieve this goal. They can be deployed in the cloud. They can have their impact on the core, managing the core and organizing it and optimizing it, especially considering the fact that we have massive amount of data these days, and this data is like passing through the network. And if we deploy machine learning AI techniques, we can make these techniques utilize these massively generated amount of data that can prove to be useful in generating some knowledge that can help optimize the network and reduce the cost and make things much better than it was before. So, speaking about machine learning, I strongly recommend you guys, the ones who want to develop good solutions that are gonna make an impact in the Open RAN system, to develop solution utilizing machine learning. So I recommend you to revise machine learning material, to return back to it and think of what solutions, what techniques, what methods we can use in order to improve the overall performance of the network. So what you need to do is to pick up a problem here. That's hopefully you select a problem related to optimization or automation or management, because machine learning and AI is good in this field. And you see any problem that you think is difficult to manage, or you hear people complaining about it, and take it and try to reduce its complexity using any of these methods or techniques which are machine learning driven. And this slide also collects and put most of the machine learning techniques and methods in one slide for you, and summarize it for any beginner to help him decide which algorithm he needs to use in order to achieve a certain functionality. So, for example, if you want to discover a structure from the data that you collected about your sites in the network, so you would, of course, use k-means method. If you want to find unusual data points, you would use machine learning algorithms like PCA-based anomaly detection or one-classes VM. If you want to predict values, you will resort to regression algorithms, ordinal regression, Python regression, fast linear regression, Python neural network regression, decision forest regression, boosted decision tree regression. All these are possible techniques, and all of them have their pros and cons, and some of them are good in accuracy, some of them they have low cost training. So you need to just decide based on your use case and the application and the requirements. If you want to predict categories, let's say classification problems, multi-class or two-class only, you have this list of algorithms that you can utilize and use. And luckily, all of these algorithms are already implemented in the cloud, like Azure or Google or Amazon. And all these algorithms are functions basically, and their input is data with some parameters and some functions, and you run it, you get a solution. So it's not difficult if you have the required data to come up with a good solution that can have huge impact on optimizing your wireless networks. So these are backup slides for synchronization issues for your reference if you want to, and these are some good links as references where you can resort to them at any time you want, especially if you want to learn step by step how to build a private 5G network, or learn more details about Open RAN, the ecosystem, the companies, the existing solutions, and building platforms for Internet of Things infrastructure.